We now start section 5.2 on power and polynomial functions. So we'll start with power functions, and I'll maybe give you some examples. So for instance, suppose you have got a circle with a certain radius r, okay? We could investigate the area of that circle as a function of r. We could also investigate the perimeter. We'll start with that, perimeter. So the perimeter would be a function of r, depending on what r is. And if you remember what the formula is, this is 2 pi r, okay? We could investigate also the area of the disk. That would also be a function of r, and the formula for that is pi r squared. And then we could also investigate the volume of a sphere, okay, of radius r. So now that's a sphere. So the volume, and there's also a formula for that, which is also just a function of r. It's a function of r because r completely specifies what the sphere looks like. And that's 4/3 of pi r squared, or cube, sorry. Okay, so it doesn't matter what the units of r are, just so this would be in units, this would be in units squared, and this would be in units cubed. So if it's r is in centimeters, then the volume would be in centimeters cubed. Okay, so what do we see actually from this is that each time we've got a coefficient standing in front of r raised to some power. So here the power is 1, here it's 2, here it's 3, and every time that power of r is multiplied by some number that we're going to call a coefficient. Okay, so we've got a coefficient here. And this is a power of r. Now, could happen also that that power is not a positive power of r. It could be a negative power of r. Maybe I'll give you another example for that. So let's say you've got, the Earth. Okay. So imagine this is the Earth here, okay, with the continents, and you've got some astronaut that's over here, okay, that stands at a distance of r, maybe not r, we're all, yeah, why not, or d, a distance of d from the center of the Earth, okay. Well, there's the Newton gravitational law of that specifies that the force, so there's something called the force. Okay, doesn't matter. Like maybe you've heard the term before. Anyway, it's a physical quantity, and if the force between two objects depends on the distance between them. So actually, d here, f of d, and that's equal to, that force is equal to some constant g. It's called the gravitational constant, times the mass of the first object, let's say the astronaut, then the mass of the second object, let's call it little big M, so big M because the Earth is bigger, I guess that's why it shows it that way. And the force is this constant divided by d squared. So in other words, it's actually some coefficient, okay, gravitational constant times the product of their mass times d to the minus 2. So here we've got a negative power, and that's also a power function. Okay, so all of these are possible, and in all these cases the power is an integer, but it doesn't have to be. It could also be a fractional number or even a real number. Okay, so a power function is of the form f of x equals k times x to the n, okay? And here the coefficient can be any real number, And the power also could be in any real number. And okay. So maybe some examples. You could have a linear function like that. Any linear function that has a y-intercept of 0 would be a power function, where the power is, or the exponent is 1. You could also have, so in general, we could have like any function of the type mx, you know. We could also have f of x, which is just the standard parabola, okay, like that, or a cubic function, could be that, okay. It could also be a reciprocal function like this, 1 over x, which is x to the minus 1, okay, in this case n is minus 1. We could also have a power function like this, maybe let's make it a 4 just for fun, x to the minus 2, okay. Those are all functions in our toolkit functions. Those are all power functions. There's another one in our toolkit functions, the square root function. That's x to the 1/2. So as you can see here, the power is, the exponent is a fractional exponent. That's allowed. We could have x to the minus 1/2, okay, combining a fractional power with a negative power. So all of these are power functions. So maybe just to illustrate their graphs, we could have all sorts of graphs. For example, this is in Desmos. As you can see on the left-hand side, f of x is kx to the n, and I can fix the values of k and n. Right now they're both at 1 and 1. So right now you're looking at f of x equals x, okay, which is a straight line with a slope of 1 passing through the origin. If I change n to 2, now we've got the parabola. Change n to 3, you've got the cubic function. Okay, let's go back maybe to the parabola. If I make the coefficient negative, what happens? Well, every y coordinate is now going to become negative. So we're going to flip around the graph about the x-axis. Okay, if k is minus 2, it just makes it a bit steeper. I could go back and set k to 1 and to 3. So now it's the cubic function. Once again, if I change k to negative 1, we're just flipping around the graph of the cubic function about the x-axis. A function that's not a power function, it would be the function like 2 to the x. Okay, g of x is 2 to the x. That's not a power function, because for a power function, the variable is in the base, not in the exponent. And this is what's happening here with 2 to the x. Okay, so in particular, 2 to the x, you notice there's an asymptote. So it reaches the x-axis really close when x becomes negative. And that's not a behavior you're going to see for power functions. One other thing I'd like to show you is the long-term behavior of these power functions. What I mean by this is what happens when x is really large or really large positively or really large negatively. And let's go back and look at the current graph, which is the graph of f of x equals x. Okay. So as you can see, when x is large, we're going to have large values of f of x. In other words, for large values of x, you've got large values of y. And this is illustrated on the graph because you end up with a curve in the upper right corner. Same happens if you've got large negative values, then you end up in the lower left corner, right? So you're going to have large negative values. So when x is large and negative, so is f of x. And if we look at n equals 3, so if the exponent is 3, you've got the exact same behavior. So when x is large positively, you've got large values of f of x. But when x is large negatively, so okay, so imagine minus 10, okay? So now we're looking at the cubic function. So minus 10 raised to the power 3, right? That's going to be minus 1,000, okay? So we're going to have large negative values. So the cubic function and the function f of x equals x have the same behavior at infinity. So when x is large positively, you've got large positive values of f of x, and when x is large negative u, you've got large negative values of f of x. And that happens again if you've got an even a power of 5. So once again, if you've got an odd power, when x is large and positive, you're going to have large positive function values. So and when f is large and negative, you're going to have large and negative values. Okay, that's due to the fact that if you raise a negative number to a large if you raise a large negative number to an odd power, you're going to get a negative large number. Okay, and let's look at even powers now. So if I choose n equals to 2, we have the quadratic function f of x equals x squared. Now on both sides, if we have large negative or positive values, the function values are going to be both positive. That's due to the fact that if you raise something to the power of 2, if you square something, you're going to get a positive number each time. Okay, so if I square minus 100, I'm going to get 10,000. I'm going to get a large positive number. So this is why you see that on both sides, the curve goes towards large y, large large y values. Yeah. So the curve on both sides basically goes all the way up. Okay, and that's going to happen again if you've got n equals 4. Okay, so now we're looking at x to the 4. It's still going towards infinity as x goes either towards plus infinity or minus infinity. Okay, so if we go to the left or to the right, the curve actually shoots up. One other feature is that as you increase the power and keep it even, so here we went from x squared to x to the 4. Notice how much flatter it is at the origin. So this is a feature that's going to show up. If I move from 4 to 6, it's going to be even flatter. See, it's even flatter now at 0. That's due to the fact that if you're raising small numbers to large even powers, you're going to get positive numbers, but are going to be pretty close to 0. Okay, and even closer to 0 as the power is large, because imagine like if you've got 1/10 and you raise it to the power of 2, you get 1 over 100. But if you raise it to the power of 4, you get 1 over 10,000, which is much smaller. So that's why it's getting closer to the x-axis near the origin. But again, as we move away from the origin towards large positive values or large negative values, it shoots up. Okay, it's going towards infinity on both sides, as opposed to like I said before, odd powers where it goes to infinity on one side and negative infinity on the other side. Okay, so we looked at 6, look at 8. It's even flatter. Okay, so as you alternate between even and odd powers, okay, you're gonna have alternate between some sort of V shape and some sort of S shape. Okay, so S, V shape again because n is 4, and S shape again because n is 5, and so on. Okay. So to summarize, this is maybe a table you want to recopy in your notes. So if we're looking at the graph of f of x equals kx to the n, so here we're going to look at positive integers above 2 or equal to 2. If we've got an even power and with a positive coefficient k, the graph is going to have this V shape that I was talking about. As you increase the value of n, it's going to get flatter and flatter near the origin. Okay, for an odd power, you're going to have this S shape that I was talking about earlier on. And same happens if the power is larger, it's going to get flatter and flatter near the origin. Okay, so notice how one is symmetric about the y-axis. That's the even power. So that's due to the fact that in this case f of x is equal to f of minus x. And notice how these S-shape, they are symmetrical about the origin. Means that if you've got a point there, you reflect it across the origin, you're going to find another point there on your curve. So that's due to the fact that f of minus x is minus f of x. Okay. Maybe I'm going to add more stuff, so I'm just going to move that down. Other things to notice are the long-term behavior. So as x goes to infinity, f of x goes to infinity as well. So this is a new notation, by the way. Notice I'm using these arrows. Okay, that actually means tends to. Okay, so this is why I don't want you to use arrows, because it has a precise meaning in mathematics. So you can read this as x tends to infinity, f of x tends to infinity as well. So this means when x is large, f of x is also large. Okay, so this is explaining this behavior here, and we're going to explain this behavior here with another statement where we're going to write when x goes to minus infinity, f of x goes to infinity. Okay, and I'm going to write down the same thing for our odd powers. As x goes to infinity, f of x also goes to infinity. And as x goes to minus infinity, now what happens is that f of x goes to minus infinity as well, because I'm going to end up here, okay, with large negative values. So I've got f of x going towards, this time, minus infinity. Okay. For if you've got negative coefficients, negative coefficient k is less than 0, you're going to have similar graphs, but this time they're going to be flipped around the x-axis, because all of a sudden all the y-coordinates become negative. So it's going to look like this, and these are going to look like this. This one is an inverted S shape like that. Okay. Again, you've got f of x equals f of minus x, because it's symmetrical about the y-axis. Here you've got f of minus x equals minus f of x, because once again, it's symmetrical about the origin. So if you've got a point here, if you reflect it about the origin, it's going to end up there on the curve as well. Here, as x goes to plus infinity, we end up with large negative values, right? The y values are negative there, then f of x is going towards minus infinity. And same happens if you go towards minus infinity, f of x also goes towards minus infinity. For an odd power with a negative coefficient, when as x goes to plus infinity, f of x now goes to minus infinity, because we end up here, right? And as x goes to minus infinity, we end up to plus infinity. Okay, so this is not something you need to remember by heart at all. Okay, so if you understand what the graphs look like, okay, even power, you only need to know the top two graphs, right? Even power is a V shape, odd powers it's this S shape, and from this you can recover the long-term behavior. And if you've got negative coefficients, you just need to know that you flip the graphs around the x-axis. So no need to remember all this. Okay, this is just pure logic. Okay, it should be pretty easy to remember. And for even an odd powers, like they connect the graphs to x squared and x cubed, right? So as long as you know those two, I mean, you're good with any power of any positive power of x. So we're just going to finish this video with a simple example here. We're going to find the end behavior of a power function. F of x equals to minus 7x to the 9. Okay? So, well, how do we do this? Well, first of all, we're going to notice that n is odd. Okay, the power, we've got an odd power, and the coefficient is negative. So for an odd power, we know it's going to look like the graph of x cubed. Okay, so x to the 9 is going to look similar. But if I have a negative coefficient in front of it, okay, it's going to flip the graph around the x-axis, because now all y coordinates become negative. So now we become negative here, and we were negative before, so we become positive over there. And from this, we can easily recover the long-term behavior just looking at how the curve behaves at both ends. So when x is large and positive, then, so I'll write that, then f of x is going towards minus infinity. If x goes to minus infinity, then f of x goes to plus infinity. Okay, and we could always verify this by verifying with some numbers. For example, f of 10. Okay, f of 10, I should get some large negative number. Let's check. F of 10 is minus 7, 10 to the 9, right? That's minus 700 million. That's pretty large and negative. If I look at f2 of minus 10, that's going to be minus 7, minus 10 to the 9, and that's minus 7 times minus 1 to the 9 times 10 to the 9. Minus 1 to the 9 is minus 1, so that's going to become 7 times 10 to the 9, so that's 700 million, and that's large and positive, as you can see. It verifies these two statements that I've made here. So no need to put this in your solution, but just know that on an exam, you can always do this verification just to see that what you wrote actually makes sense.